Hey you guys, this is Mr. Millings, and in this video we are going to learn about the ideal gas law. So what is the ideal gas law and how does it work? Well, it says right here that the ideal gas law is a gas law that takes into account the pressure, volume, temperature, and number of moles of gas. Furthermore, it says right here that an ideal gas is a hypothetical gas in which things like intermolecular forces do not exist to complicate the simple ideal gas law. So essentially, the ideal gas law is a gas law that we can apply to gases that behave, as we say, ideally. And an ideal gas is basically a gas in which the intermolecular forces aren't taken into consideration when we're talking about that gas. All right, so the ideal gas law, once again, is a gas law that takes into account things like pressure, volume, temperature, and number of moles of gas into one easy to use little formula. So the ideal gas law basically tells us that pressure times volume equals the number of moles of that gas times the temperature of that gas times some sort of constant, in this case the universal gas law constant. So PV equals nRT, and when we're working with the ideal gas law, it's important to keep in mind that the pressure always needs to be in atmospheres, the volume always needs to be in liters, N stands for the number of moles of gas, the temperature always needs to be in Kelvin, and last but not least, R, the universal gas law constant. What is this here? Well, this is a constant that ties the number of moles and temperature and volume and pressure of a gas together somehow. And so this is always going to be the same number, and the universal gas law constant is 0.0821 liter atmospheres over moles Kelvin. And this funky little unit right here allows us to cancel out all of these other units of temperature, moles, liters, and pressure or atmospheres when we're working with the gas law or the ideal gas law formula. So let's go ahead and apply this ideal gas law formula to 4 different sample problems, and hopefully you catch on. In this first example, it says a 6,860 milliliter flask contains 31.3 grams of oxygen gas at a temperature of 37.7 degrees Celsius. We want to calculate the pressure inside of the flask in pounds per square inch. So if we take a look at this problem here, milliliters is a measurement of volume. Grams, well, we don't see grams in the ideal gas law formula, but we can convert these grams to moles, no problem. We see that we have degrees Celsius, which is a measurement of temperature. We're asked to figure out the pressure. So what formula do we know uses P, V, N, and T? That's going to be the ideal gas law, PV equals nRT. However, when we work with this formula here, the pressure always needs to be in atmospheres, the volume always needs to be in liters, the temperature needs to be in Kelvin, and this right here is the number of moles of gas. And then this here is your universal gas law constant, which varies depending on what type of units you are using. So if we take a look here, we're trying to figure out the pressure in PSI. The volume, it tells us, is 6,860 milliliters. The number of moles here, well, we have 31.3 grams of O2. We're going to convert this to moles here momentarily. And then our temperature here is 37.7 degrees Celsius, which we will have to convert to Kelvin. Once we do all of that, we can plug it into this formula. So this is the same thing as 6.86 liters. If we divide by 1,000 to convert milliliters to liters, that's our answer. If we take a look right here, we need to convert the grams of oxygen to moles of oxygen. We know 1 mole of O2 is 32 grams of O2. And how did we get this? 2 times 16 from our periodic table, which is the molar mass of oxygen. And so when I put this in our calculator, I end up with 0.9781. 0.9781 moles of O2. And so when we're doing these conversions before we plug it into the formula, we're going to want to keep as many of these decimal places as we can. So that way our final answer is accurate, right? So we're going to go ahead and just round to the 10,000th place here. Right here we have the temperature in Celsius. Temperature needs to be in Kelvin, so we're going to add 273 to this. And if we add 273 to that, we're going to end up with 310.7 K. There, so we have our volume in liters, we have the number of moles, we have our temperature in Kelvin, and we're asked to figure out the pressure. So we know that PV equals N times R times T, and we're asked to figure out the pressure. So we're going to divide both sides by V. V is going to cancel here, and so the formula that we're going to use to solve this problem is the pressure equaling N times R times T all over V. So if we take a look, the number of moles of this gas is 0.9781 times R. R is going to be our universal gas law constant, which is 0.0821 liters times atmospheres over moles times Kelvin. The temperature of this gas is 310.7 Kelvin. And the volume of our gas is going to be 6.86 liters. And so now we'll put this in our calculator. 0.9781 times 0.0821 times 310.7 divided by 6.86, and we end up with an answer of 3.637. 3.637 what? Well, let's see what cancels out. Moles is going to cancel out here. We have Kelvin canceling out with this Kelvin. We have liters canceling out with this liters, leaving us with atmospheres. So this is not our final answer because it wants the pressure in pounds per square inch. So we have to carry this a step further. Whoops, to get the pressure here, we're simply going to take the atmospheres, which is 3.637 atmospheres, and do a little dimensional analysis. We know that 1 atmosphere, 1 ATM, is 14.69 psi. And so we multiply these two numbers together, and we're going to end up with a final answer of 53.4, approximately 53.4 psi. So that is going to be the pressure of the oxygen gas that is inside of this flask right here. Keep in mind also that oxygen gas is diatomic. It's one of those 7 diatomic molecules from the periodic table, so it always exists as O2 when it's not bonded to another atom on the periodic table. So that's where we got O2 and the molar mass of 32 for the number of moles when we calculated the number of moles right here. Let's take a look at another example. In this second example, it says a 55-gram sample of fluorine gas has a pressure of 396 torrs and a temperature of 212 K. Calculate the volume of the gas in milliliters. So if we take a look right here, we know the number of grams of this fluorine gas. We can easily convert this to moles, or N. We know the pressure of the gas is right here, 396 torrs, and it has a temperature of 212 K. We want to calculate the volume of this gas in milliliters. So what formula do we know uses PV, N, and T? That's the ideal gas law. PV equals nRT. And once again, pressure always needs to be in atmospheres here. The volume always needs to be in liters. And the temperature always needs to be in Kelvin when we're working with this formula. So let's see what we're dealing with here. We have P, we have V, we have N, we have T. And so let's take a look at this word problem and figure out what's happening. The pressure here is 396 torrs. If we take a look, the volume here is what we're trying to find, and we want to figure it out in milliliters. The number of moles, well, that doesn't give us the information directly in the problem. However, we have 55 grams. We have 55 grams of fluorine. Now, fluorine is another one of those diatomic molecules. So F2 is its chemical formula. Remember Haber-Finkel, the 7 diatomic molecules. And then the temperature here, it tells us, is 212 K. So our temperature unit is okay for this ideal gas law. Let's see right here. The pressure, though, is in torrs, so we need to convert this to atmospheres. So how do we convert this to atmospheres? Well, if we take 396 torrs, we know that 1 atmosphere is 760 torrs. And so we will end up with 0.5211. 0.5211 atmospheres. If we take a look, we're trying to figure out the volume in milliliters. We need to convert the grams of fluorine now into moles. We know 1 mole of F2 from our periodic table of elements is going to end up to be 38, I believe, 38 grams of F2. Fluorine's molar mass is 19 on the periodic table, and 19 times 2 is 38. And so if we put this in our calculator, we end up with 1.447 moles. 1.447 moles of F2. And our temperature is in Kelvin, so we're good. We can now plug this stuff in. We know that PV equals N times R times T. And in this problem here, we're asked to solve for V this time, so we're going to divide both sides by P. P is going to end up canceling here. And so it looks like to figure out the volume, we'll have to take N times R times T, all divided by P. So N in this problem, if we take a look, is 1.447 moles. R is always the same thing, 0.0821 liter atmospheres over moles Kelvin, times the temperature, which is 212. And we're going to end up dividing this by the pressure, which it tells us right here is 0.5211 atmospheres. So now we get our calculator out. We take 1.447 times 0.0821 times 212, and we're going to divide this by 0.5211, and we end up with an answer of 48.3. 48.3 what? What unit is going to get attached here? Well, if we take a look, atmospheres is going to cancel, moles is going to cancel, Kelvin is going to cancel, leaving us with liters, but we want the final answer in milliliters. So how do we convert milliliters to liters? Well, we have to multiply by 1,000, right? Or if we set the dimensional analysis up, we know that there are 1,000 milliliters in one liter. So essentially slide this decimal to the right 3 times and we will end up with our final answer. 48,300 in milliliters. 48,300 milliliters will be the final volume of this fluorine gas. Let's take a look at another problem. In this third example, it says a sample of nitrogen gas has a pressure of 52.8 psi, a volume of 9.55 liters, and a temperature of 301.6 degrees Celsius. We need to determine the number of molecules of nitrogen gas. So if we take a look here, we have a sample of nitrogen gas. Its pressure is this right here. Its volume is this right here. Its temperature is this right here. And what we need to figure out is the number of molecules. So if we figure out the number of moles first, we can then multiply this by Avogadro's number and convert it to molecules. So what formula do we know uses P, V, N, and T? That's going to be the ideal gas law. And so let's take a look at what we have here. Let's take a look at our variables in this problem here and see what we need to do. So the pressure, if we take a look, is 52.8 pounds per square inch. It tells us that the volume is 9.55 liters. It tells us that the temperature is going to be 301.6 degrees Celsius, and we need to figure out how many molecules, not moles, but molecules. So if we figure out N first, we can then convert it to molecules. So keep in mind, pressure always needs to be in atmospheres when we're working with the ideal gas law. Volume always needs to be in liters. Temperature needs to be in Kelvin. And N here is the number of moles of the gas. So if we take a look, what we first have to do is convert this pressure into pounds per square, into atmospheres. And so if we take a look, we have 52.8 psi. We know that 1 atmosphere is 14.69 psi from an earlier video. So we'll take 52.8, divide that by 14.69, and we end up with 3.594. 3.594 atmospheres. If we take a look right here, Our volume is in liters, which it needs to be, but our temperature needs to be converted into Kelvin. So we're going to add 273 to this. 273 plus 301.6 equals 574.6 Kelvin. So now we have the units, how we need them to plug them into this formula. So we know that PV equals N times R times T. And in this problem here, we're going to solve for N this time. So we need to divide both sides by R and T. R and T are going to cancel. And so the formula that we're going to use to solve this problem here is going to be N equaling PV over RT. So our pressure here, if we take a look, is 3.594 atmospheres times our volume, which we see right here is 9.55 liters. And we're going to end up dividing this by R, which is 0.0821 liters times atmospheres over moles times Kelvin, multiplied by the temperature, 574.6. And so when we put this in our calculator, the way that the calculators work is you're going to have to put everything in the denominator in parentheses. If you're going to multiply these two terms on the bottom, make sure you put everything in the denominator in parentheses. So we'll take 3.594 times 9.55, and we're going to divide this by parentheses 0.0821 times 574.6. Close those parentheses, and we end up with 0.7276. 0.7276. Well, let's see what unit we need to attach here. It looks like atmospheres is going to cancel, liters is going to cancel, Kelvin is going to cancel, leaving us with moles. Of what substance? Nitrogen gas. Keep in mind that nitrogen is another one of those 7 diatomic molecules. So it's N2. But the question here isn't asking for the number of moles. We are asked to figure out the number of molecules of N2. So how do we do this? Well, we take the number of moles here, 0.7276 moles of N2, and we need to do some dimensional analysis. Right? We know that 1 mole of N2 contains Avogadro's number, 6.02 times 10 to the 23rd molecules of N2. From an earlier video, we learned how to do these conversions. And so you'll take 0.7276 times 6.02 times 10 to the 23rd, and we're going to end up with 4.38 times 10 to the 23rd. 4.38 times 10 to the 23rd molecules of nitrogen gas. All right, so there's a lot going on in this problem. A lot of conversions need to be made before you even plug it in, but there is your final answer. Let's take a look at another problem. In this fourth and final example, it says 2.59 times 10 to the 23rd molecules of gaseous krypton is in a 7,341 milliliter container under a pressure of this right here. We need to determine the temperature of the gas in Kelvin. So if we take a look, we don't know the number of moles of krypton, but we know the number of molecules. And so we can make that conversion and figure out what N is going to be. We have milliliters here, which is a measurement of volume. We have pressure here. And we have to figure out the temperature of this gas in Kelvin. So what formula do we know uses P, V, N, and T? That's going to be our ideal gas law. And keep in mind that when we work with this formula, our pressure is going to be in atmospheres, our volume is going to be in liters, and our temperature needs to be in Kelvin. So let's lay it all out. We have P, we have V, we have N, we have T. And R is our universal gas law constant. So in this problem, this is telling us that we have 471.881 kilopascals. And so what did I do there? Well, this is how many pascals it is. So I slid the decimal 3 times to the left, or divided by 1,000 to convert it to kPa, or kilopascals. The volume here is going to be, our volume here is going to end up being this many milliliters, but we need to convert it to liters, so we need to divide by 1,000 again. Slide the decimal 3 times to the left, and you end up with 7.341 liters. If we take a look, we don't know the number of moles, but we know the number of molecules. So let's figure out how many moles this is. We have 2.59 times 10 to the 23rd molecules of krypton. So let's go ahead and do our dimensional analysis right now. Give us some more room. We know that 1 mole of krypton contains Avogadro's number of krypton, 6.02 times 10 to the 23rd molecules of krypton. And so when we put this in our calculator, 2.59 times 10 to the 23rd divided by 6.02 times 10 to the 23rd, we end up with 0.4302. 0.4302 moles of krypton. So now we know N. Let's take a look at T. Oh, that's what we're trying to find. We need to figure this out in Kelvin, right? So take a look right here. Our pressure here needs to be in atmospheres. So how are we going to convert this into atmospheres? Well, if you take a look, we know that 1 atmosphere is 101.3 kPa. How do we know this? That's from an earlier video on pressure unit conversion. So we'll take 471.881. We're going to divide this by 101.3, and we end up with 4.6582. 4.6582 atmospheres. So now we can finally plug all this information into our formula here. We know that PV equals N times R times T. And in this problem here, it looks like we're solving for T. So we need to divide both sides by NR. NR is going to cancel. And so the formula that we're going to use to solve this problem is going to end up being the temperature equaling PV over N times R. And so what is the pressure in this problem? 4.6582 atmospheres times the volume. What's the volume? 7.341. What is N in this problem? If we take a look, it's 0.4302 moles. And R, what is R? That's the universal gas law constant, 0.0821 liters times atmospheres over moles. That should be an M, Kelvin. And so when we put this in our calculator, let's take a look. We're going to end up with 4.6582 times 7.341. We're going to divide this by parentheses. Remember to put everything in the denominator in parentheses when you're putting this into your calculator if you're going to multiply these two terms. 0.4302 times 0.0821. And we end up with an answer of 968.2. 968.2 what? Well, let's take a look here. It looks like atmospheres is going to cancel. It looks like liters is going to cancel. It looks like moles is going to cancel, leaving us with Kelvin. So the temperature of this gas is going to be 968.2. If you like what you see, go ahead and click that little bomb in the bottom right-hand corner. That's going to subscribe to my channel. And feel free to leave any comments or questions in the comment section down below. And I hope you guys found this helpful.